Hey guys. So, what we are doing today kind of sets the foundation for the rest of the semester. Um, I mentioned in the first lesson of this semester, we did indefinite integration. Indefinite integration is what we've been doing the last couple of classes. That's when you're given a derivative and you're trying to go backwards to find the original function. That is indefinite integration. There is another type of integration that we are now going to start to get into, and that's called definite integration. And I'll talk more about that as the notes go on, but today kind of lays the groundwork for definite integration, which is primarily what the semester is all about. So this first page of notes, here's the deal. It's all about sigma notation and summation notation. Yeah. Come to find out, we're not going to be doing any sort of sigma notation on the AP test or in tests in here. But the reason I'm showing it to you is to, first of all, refresh your memories on what it is, because those of you going on to Calc 2 at some point, Calc 2 is all about series, like adding things together, and you're dealing with sigma basically the entire time. So I want to refresh your memory on that. And number two, it's kind of where definite integration stems from is sigma notation, which we'll get into more next time. So we're not going to go through all these examples. I just wanted to refresh your memory on exactly what it's asking you to do when you see it. So this right here is known as sigma notation, otherwise known as summation notation. So when you see sigma, thinking back to algebra 2, at least I know in algebra 2 honors, I know you do it in regular algebra 2. I think you do a lot of it in I shouldn't say a lot, but you do some of it in pre-cal as well. But remember, when you see sigma, this is a command to you to add numbers together. That's what sigma means. It means I want you to add numbers together. And now you need to think, well, okay, how many numbers do you want me to add and what numbers do you want me to add? And that's what all the information around sigma is giving you. So to refresh your memory on how you figure out what numbers you're going to add, you take whatever this bottom number is. It could start as a 1, it could start as a 0, it could start as a 2, it doesn't matter. But take whatever it is and plug it into your expression. So if I plug 1 in, I get 2. That means the first number I'm going to add is 2. Then I'm going to plug in every integer all the way up until I get to 5. So like the 1 all the way up to the 5 is kind of like a counting mechanism. So now I'm going to plug 2 in for I, and I get 4. And then I plug 3 in for I. And then I plug 4 in for I, all the way until I get 5 and plug 5 in for I. So this expression here is really just telling us to add the numbers 2, 4, 6, 8, and 10 together and get a value in the end. So if I add these up, I get 30. Now, some of you learned back in Algebra 2 and maybe pre-cal that a lot of calculators have a summation button. It really doesn't matter since we're not doing a lot of this, but there's a summation button under the math menu that allows you to just enter this entire thing, push enter, and it tells you 30. But if you notice, you get a value in the end. So I want to start, we're not going to do the rest of these examples, by the way, at least on the front page. So we get a value in the end. When I mention definite integration, I want to start talking about the rest of the notes and the rest of the semester. So here's where we are headed, okay? You're going to be given some sort of curve, okay? You're going to be given a graph like this. And the question is going to ask you to find the exact area underneath that curve. So the question wants you to find exactly how much area is underneath that curve. Now, up till now, we don't know how to do that. Just like first semester, we didn't know how to find the slope at one point. That's what first semester was all about. We don't know how to find areas of weirdly shaped figures. We know how to find area of triangles and squares and rectangles and circles and trapezoids and things like that, but we don't know how to find areas of this. And this is what second semester calculus is all about, is also finding area underneath the curve. And that's why we end up getting a value in the end with definite integration. That's what it's doing, okay? So before I just, we're not actually going to learn how to exactly do that for a couple classes, okay? What we are going to start with is how do we approximate what the area might be? And that's what the rest of the notes are all about, okay? So what I have here is the graph of x squared plus 2. Okay, I have this graph right here. And it's graphed on the interval 0 to 3. And let's say the question wants us to find the exact area between the x-axis and underneath that curve. Like, I want to find this exact area right here. Like I said, I'm not going to teach you exactly how to do that today, okay? But what I am going to teach you is how we build up to how we find that exact area, okay? And what we do is what is called a Riemann sum. This is a very important vocab word. We're going to perform what's called a Riemann sum. And what that means is we are going to draw rectangles underneath this curve or above the curve, but basically we're going to draw rectangles because we all know how to find areas of rectangles. Basically, second semester calculus is all about rectangles. First semester calculus is all about slope. Second semester calculus is all about rectangles. So we are going to draw rectangles. That's when it asks you to do a Riemann sum, which I'm going to explain a little bit more here. But it basically is saying draw rectangles. And then what you're going to do is find the area of all those rectangles you draw and then add those areas together. And we say that's a pretty good approximation for the area under this curve. I'm going to get a pencil because I want to draw a few different things on here. And all I have is a pen. Okay. So when it asks you to do a Riemann sum, okay, there are 3 different types of Riemann sums they're going to ask you to do. And you don't need to draw this right now. We're going to do these examples here in a little bit. I'm just going to show you the concept in this figure. You don't need to draw anything. I just want you to watch. So there are 3 different types of Riemann sums they could ask you to do. They could ask you to do a right Riemann sum. So you could do a right Riemann sum. They could ask you to do a left Riemann sum. Or they could ask you to do a midpoint Riemann sum. And I'm going to explain what that means here, okay? I pulled out a free response question from 2015 just to kind of show you an example of what they'll do. A lot of times this gets used with table problems. But if you notice right here, it says approximate this integral using a right Riemann sum with 4 subintervals. So that's how they'll ask the question. They'll tell you exactly what type you're going to be doing. Let me explain what that means, okay? So if they ask you to do a right Riemann sum, let's say they said do a right Riemann sum with 3 rectangles, okay? So what that means is this. If I'm doing a right Riemann sum, I'm going to start at the most right endpoint on the x-axis, okay? And I'm going to go up until I hit the curve, right there. And now I'm going to go over a certain distance. Well, the distance I go over depends upon how many rectangles I'm going to draw. So let's say this problem said draw 3 rectangles over this interval. I want 3 different rectangles. Well, if that's the case, then each of my rectangles is going to be a width of 1. So I'm going to draw over until I go over 1 unit, and then I go down. And then I would calculate the area of that rectangle. We're not going to do that just yet, but that's what I would do. And then I start at 2, where I just ended. I go up till I hit the curve. I go over till I get to 1, and then I go down. And I would find the area of that rectangle. And then I would go up, and I would go over, and I would go down. And I would find the area of that rectangle. So this would be a right Riemann sum approximation with 3 rectangles, or 3 subintervals, they might say. And I would find the area of those 3, add them up, and say, there's my approximation. Now, obviously, that's a terrible approximation because look at how much excess area you have, right? We have way too much. And we're not going to do the numbers here just yet. Let's say the problem said, do a left Riemann sum. Well, let me explain what that would be doing. So if it said do a left Riemann sum, well, now I'm going to start at the most left endpoint right here. And I'm going to draw my rectangles going to the right. So a left Riemann sum, I would start at 0. I would go up till I hit the curve. I would go over, and I would go down. And then I would go up, and I would go over and down. And then up, over, down. That is the worst rectangle I ever drew, that last one. So now, if it was a left Riemann sum, I would find the area of these three rectangles, add them up, and say, yeah, that's pretty much the area under that curve. Also a terrible approximation because we're missing all of this space right here. And we'll get into that more. So that would be a left Riemann sum. And then the last one they could ask you to do is a midpoint Riemann sum. Here's what this means. If they say do a midpoint Riemann sum with three rectangles, well, my rectangles are still going to be like from 0 to 1, 1 to 2, and 2 to 3, but the rectangles are going to hit the curve at the midpoints of these intervals. So instead of hitting at 0 or at 1, at 0.5, my rectangle is going to hit the curve, and then I just draw the top base from 0 to 1 right here, and I draw my rectangle. So the rectangle is hitting the curve at the midpoint of my intervals. So at 1.5 right here, it would hit the curve. I'd go up till there, over, and down. And then at 2.5, I would go up, over, down. So here's an example of a midpoint Riemann sum. So again, I'm just trying to show you the concept of what they're asking you to do when they use that terminology. You do a right Riemann sum, do a left Riemann sum, do a midpoint Riemann sum. So now let's do it. Let me show you, the concept in action and then putting the numbers to the problem. So this function, again, all the problems we're doing today are the same equation of x squared plus 2, which is going to be important here in a second. Okay. So this one says, let's approximate the area using three rectangles or subintervals and their right endpoints. I should have changed the terminology here. I should have said do a right Riemann sum with three subintervals, just so you guys can get used to that terminology. A right Riemann sum is what this problem is asking us to do. So again, just like I did up above, I'm going to start at 3 on the right endpoint. I go up till I hit the curve. I go over till I get to 2, and I go down. Okay, now the question is, how do we find the area of this rectangle? That's the whole point of this lesson, is we're finding areas of rectangles and then adding them all up. So our area is going to approximately be this. Well, I want to find the area of this rectangle. Now, an AP tip for you guys. I know you could do a lot of mental math, but I also know when they ask you to do a Riemann sum problem, they want to see the lengths and widths of the rectangles that you are multiplying. They don't want you to just do that quick multiplication in your head. That's how you'll earn points, is by showing the length and width being multiplied. So the width of this rectangle is 1. And now I need the height of this rectangle. If I know the height, then I know what the area is. So let's think about this. This is basically the hardest part of the problem, and it's not even that hard. I want to figure out how high this rectangle goes. Well, notice where my rectangle is hitting the curve. It's hitting the curve when x is 3. So what I need to find is the y value of this function when x is 3. Whatever this y value is here, that's the height of the rectangle. So plug 3 into our function right here, and whatever that is, that's our height. So if I plug 3 in, I get 11. So that means this rectangle goes up to 11 units. So 1 times 11. And I wouldn't just write 11. I wouldn't do that in my head. Now I go at 2, and I go up till I hit the curve. I go over, and I go down. And now I want the area of that rectangle. We're going to add that to the previous one. So the width, again, is 1. But now notice what the height of this rectangle is. So this rectangle is hitting the curve when x is 2. So I plug 2 into the function, and I get 6. And then I draw my next one. The width is 1. The height, well, now I need to find the y value of the function when x is 1, so 3. Now, if this is a free response question, you're allowed to leave this answer. Remember, you don't have to simplify any numbers. Like if you get some messier numbers here, these are pretty easy to deal with, but if you get some messier numbers, you're allowed to just leave this and be done with it. I'm going to add this for conversation purposes. You'll see here why. So this is about 20. Now, think about what we're approximating. We're trying to figure out what is this exact area under the curve. 20 is our first approximation. That's a terrible approximation because look at how much extra area we got that we don't want. We got way too much. But here's at least what this does for us. at the beginning, we didn't have a clue what the area of this under this curve was, but we at least now know the most it could possibly be is 20. Because with the area of these rectangles, we got everything we wanted and more. So this is known as an upper bound. Meaning we had no clue what it was before, and now we at least know it has to be under 20, which is not a great approximation, but it's a starting point. Okay, so I want to talk about something we did first semester and relate it to questions they'll ask here, okay? So if you think back to first semester, I want to refresh your memories that, do you remember those problems where they would say, do a tangent line approximation, and then they would ask if your approximation was an overestimate or an underestimate to the actual value. And I want you to think about what determined if the tangent line was an overestimate or an underestimate. Remember that if a function was concave down, and the problem would tell you, they would say, let f be a concave down function. They would give you that info. But if a function's concave down, a tangent line will always overestimate. A tangent line will always be above a concave down function. Or if a function's concave up, a tangent line is always below. It's an underestimate. Well, they're going to ask you that same question with Riemann sum problems. They're going to say in the problem, do a right Riemann sum with 3 rectangles or 4 rectangles or whatever the case may be. And then they're going to say, is your approximation an overestimate or an underestimate? They're going to ask that of you. And a lot of times you're going to do these problems without a graph. You can't just say, well, look at the graph. They're going to give you a table. And we have to know what information determines if a right Riemann sum overestimates and underestimates, and if a left Riemann sum overestimates and underestimates. And I want you to think about what might be true about the function that would determine if a left Riemann or right Riemann would be above the curve or below the curve. And I asked this in my other classes when I was able to be here. And a lot of times they would say, well, the concavity. Maybe it's the concavity. And I want to show this to you. I don't have these memorized personally. Like, I don't know if the question really quickly says, let f be an increasing concave down function, do a right Riemann sum estimation, is your estimation above or below? Like, I don't know. But here's what I do to get to the answer. I want to give you some advice here. I draw the 4 pieces of the scenarios of what the graphs could possibly do. I basically take my 2 parabolas, my downward parabola and upward parabola, and split it up. And so now I have all 4 scenarios represented. I have an increasing concave down, I have decreasing concave down, I have increasing concave up, decreasing concave up. And I want you to look at what I'm about to do. And I do this every time they ask these questions. I draw these 4 pieces, and I fill in my scenario. So I'm going to really quickly do a right Riemann sum underneath every one of these pieces. And here's what I mean by that. So I start at the right, I go up, I go over, I go down. I start at the right, I go up, I go over, I go down. It doesn't matter where you start, as long as you go up and then draw your rectangle to the left. I go up, I go left, I go down. Up, left, down. So I just did a Riemann sum on all 4 of these parts. And I want you to notice that if a function is concave down, well, here Riemann sum is underneath the curve, here it's over the curve. So here it underestimates, here it overestimates. So it's not the concavity that matters. Same thing down here. What matters is if the function is increasing or decreasing. Notice that if a function is decreasing here and here, a right Riemann sum will underestimate the actual area. And if a function's increasing, a right Riemann sum will overestimate the actual area. And you would flip that for a left Riemann. Again, I don't have those memorized. But if they ask the question, I have a 20-second way that I know how to answer the question. And the problem will tell you. They'll say, let f be an increasing function. Do a right Riemann sum approximation. And since it's increasing, then I know a right Riemann sum would overestimate just by looking at these pictures right here. So that's a question very commonly asked on the AP test and on your quizzes and tests that I'll ask you in here. Okay. All right. So that was a right Riemann sum. Let's do a left Riemann sum. So now for a left Riemann sum, I start at the left endpoint, I go up, I draw to the right, I go down. And I want to find the area of that rectangle. Notice what's different on this one. So my width is still 1, but my height now, notice that my height is hitting the curve when x is 0. So I plug 0 into the function, which is x squared plus 2, and my height is 2. I didn't use that height on the right Riemann sum. And then I draw the next rectangle. Start at 1, go up, go over, down. So my width is still 1, and my height is whatever f of 1 is. Plug 1 into the function, you get 3. And then up, over, down. Width is 1. Height is whatever f of 2 is. My rectangle's hitting the curve at 2. So 6. So notice what happens versus a right versus a left Riemann sum. If you're doing a right Riemann sum, it's the most right function value that will be there. The left endpoint will not be. If you're doing a left Riemann, then the most left y value will be there, and the right one won't be. So that's what happens. All the middle ones will be in play. So I add these up, and I get 11. Also a terrible approximation because we're missing all this stuff right here. But at least I know every single one of these rectangles is below the curve, so this is the least amount our area could possibly be. That's known as a lower bound. So we got two different terrible approximations here, but we at least now have a range of what the exact area is. We know the highest it could be is 20, the lowest it could be is 11, just by drawing 3 rectangles in there and finding the area of those 3 rectangles. So, hey, we got somewhere. All right, the last Riemann sum they might ask you to do is a midpoint Riemann sum. This one's a little tougher just because a lot of times you're dealing with not as nice numbers. So let's do it. So when we do a midpoint Riemann sum, my rectangles, like I said earlier, are still going to be from 0 to 1, from 1 to 2, from 2 to 3. But now instead of my rectangle hitting at 0 or at 1 or whatever, it's going to hit at 0.5. So I go at 0.5, hit the curve there, and then draw the top of my rectangle from 0 to 1. That was not a great rectangle, but whatever. So now my area, the width is still 1, but my height is whatever the function value is at 0.5. So I would plug 0.5 into my function and get the height. So that would be 0.25 plus 2, 2.25. Plus, well, now I'm going to draw my second rectangle and hit it at 1.5. So the width is still 1. But now I plug 1.5 into my function. 2.25 plus 2 is 4.25. And then plus, I hit at 2.5. So 1 times 8.25. And then I add those up. So that's 12.5, 14.75. And that's actually not a bad approximation because if you look, like each one of these rectangles, this one goes a little over and then it's also a little under. This one goes a little over and under and over and under. And it looks like those areas they're not the same, but you know, they're fairly close. So not a bad approximation there. So what happens if we would use more rectangles than just 3? What if we put 6 rectangles in here? What would happen to those approximations? And I did this in class the other day, and then the class started groaning because they've had enough of drawing these rectangles and finding areas, and now we're going to do the same thing with 6 of them. Well, where we are headed is, eventually, we are going to fit infinitely many rectangles inside of here and find the area of every one of those rectangles, and then add the area of every one of those infinitely many rectangles together. That's where we are headed. Obviously, we're not going to do that by hand, but that's what definite integration is going to do for us. We're going to basically fit infinitely many rectangles under the curve. Because you're going to see what happens here when I fit 6 rectangles in. So if I do a right Riemann sum with 6 rectangles, well, now all that changes is the width. If I need to fit 6 rectangles in here, now the width of every one is going to be 0.5. So I start at 3, I go up, I go over till 2.5, and I go down. And then I would go up, and I would go over till 2, and I'd go down. And I'm going to find the area of all 6 of these rectangles. I'd go up, over, down, up, over, down, up, over, down, up, over, down. And what you notice here is it's actually a better approximation than just putting 3 rectangles in there. You know, when I put 3 rectangles in, look at how much space was above the curve there with 3 rectangles. And now when I put 6 in, they're all still above. Like, this is going to be an overestimate, but all that area combined is not as much as what the other one was. And when I find the area of all these 6 rectangles, so now my widths are all going to be 1/2. So 1/2 times the height at 3, which is 11. My next rectangle is 1/2 times whatever the height is at 2.5, so 8.25. I have my key right here, that's how I'm going to get these numbers really quickly. The next one's 1/2 times whatever f of 2 is, so 6. 1/2 times, well, 1.5 squared plus 2 is 4.25. And then 3. And then 2.25. So again, when you're doing a right Riemann sum, that most left y value doesn't matter because your rectangle doesn't hit the point. Like, I don't find f of 0. I find f of 3 and then all the other ones. And I get this. And when I do that calculation, I get about 17.375. So when we did 3 rectangles, we got 20, which was an overestimate. Just by putting 3 more rectangles in there, we cut off about 2.625 units of what the area could possibly be. This is our new upper bound. Just by putting in 3 more rectangles, we cut off a whole lot of that excess area. Imagine putting in 1,000,000 rectangles, which is what we are going to be doing. On the AP test and on questions I'll ask you, I don't know about the homework exactly, but on like a test or a quiz, it's very common that you have to do 4. That is the most common number they do, is you'll have to find the area of 4 rectangles. So it's not too bad if they ask it of you on the AP test. And then the left end points, I would do the same thing. I would draw 6 rectangles of 1/2 width, so f of 3 won't matter. I'm just going to put those numbers up there so you could see it right here. But notice when I do a left Riemann sum on an increasing function, it's an underestimate. And we get a new lower bound. So before we were between 11 and 20, now we're between 12.875 and 17.375. So we're getting closer just by having 6 rectangles in there. Woohoo! You guys have a fantastic day. You're all awesome.